Hello everyone, it's me, Mr. Younger again. I am here to work yet another example of a calculation of center of mass. This is a calculation of center of mass that will involve using the calculus. So let me go ahead and get started by sharing my iPad screen with you. All right, so we have the actual iPad screen showing, and you can see I've already typed up a specific problem to solve. It says a right triangular shaped plate has a height h, a width w, a negligible thickness t, a mass m, and is made of material whose mass is uniformly distributed, i.e., it's a homogeneous lamina. Homogeneous means it's uniform all the way throughout in every direction, basically. And lamina means it's a two-dimensional object in some sense, or at least we're treating it that way. This also means its density is a constant. What we're asked to do is put it in a coordinate system and compute its center of mass, and that's what I'm going to do now. In fact, I'll start off by treating it as a or three-dimensional object, which it really is, and then show you how we're just going to continue as if it's not. In some sense, we could sort of work the problem two ways. One way where it's two-dimensional, and one way where it's three-dimensional. So I'll give you enough of information about the three-dimensional case so you know where to go if you wanted to continue it as a three-dimensional problem. So let's start off by writing a solution. The solution, remember, I usually write that out to list the equations and the variables we know. So the variables we know are we know H, we know M, or excuse me, we know W, we know thickness, T, we know uh, M as well. And then from that, we know, for instance, that the area of the plate would be one half height times width. We know that the volume of the plate would actually be one half height times width times thickness. Those are various things we know. And we also know that the x center of mass can be calculated by using the integral of uh, x dm divided by the integral of dm. And we also know that y cm is equal to the integral of y dm divided by the integral of dm. And we know that we have various ways to specify dm. Dm can be, for instance, equal to lambda times a differential length if it were a one-dimensional object. It can also be a sigma times a differential area element if it's a two-dimensional object, which is what we're going to try here. And then if you want to recognize it as the real three-dimensional object it is, we could also say that it is equal to rho. That's the normal density that we're used to in everyday life and chemistry and stuff like that, times the differential volume element dV. So those are the different things we can use. Given the three-dimensional case and the two-dimensional case, I'll go ahead and say three dimensions are three-dimensional. Uh, that tells us that the mass or that the density is equal to mass over volume. And that would mean it actually has a density given by m divided by one half h w times t. Or if we did it in two dimensions, we would say the density is actually an area density, which is area, or excuse me, which is mass divided by area, which in this case would be m divided by one half h omega, excuse me, without the t. So those are the two potential scenarios. I do have to embed this in a coordinate system. So I'm going to choose a specific coordinate system that may or may not be the nicest one, but that's okay. I want to make sure you guys have some experience with a non-trivial example of calculus calculation of the center of mass. So I'm going to go ahead and draw my y-axis, and I'm going to draw my x-axis, and I'm going to call this my x-axis, and I'll call this my y-axis. And in fact, the actual object is going to be, I probably should have used a nicer drawing there. This is going to be our actual plate, like that. And specifically, this right here will be the dimension W. This dotted line shows us that the height is h equal y. And of course, the origin has the other tip. But that's basically it. In principle, it does have a thickness, of course, T that you can sort of imagine going into the Z direction. If it came out, if you said this was, for instance, the back surface of the plate, then the front surface would be in the positive Z direction. But if you said that drawing that I have there is the front surface of the plate, then the thickness would be in the negative z direction. Again, remembering that our coordinate systems, our Cartesian coordinate systems, should be right-handed, and that means if you take the curl of x cross y or I hat cross j hat, you get z pointing out of the board. So, anyways, that might be too much information that you didn't necessarily want to know, but it is important to remember that our coordinate systems should always be right-handed, and the way to do that is use your right hand like this and recognize your index finger can be the x-axis, your middle finger, which is perpendicular to the index and the thumb, is your y-axis, and then your thumb, which is perpendicular to the index finger and the middle finger, is the z-axis. So if you have it in this orientation, it will automatically be a right-handed coordinate system unless you mistakenly use your left hand. All right, so let's go ahead and try to figure out what the x center of mass is. I've already calculated the density, and we are working this as a two-dimensional problem. So I'm going to follow up and just write that this, in two dimensions, this density becomes 2m over h W like that. We might use that later. The main reason I even wrote all this, because I really didn't have to technically calculate it, but the main reason I wrote it was so that you, my students, and anybody else in the world that might be watching this video will have some understanding of what I mean by sigma and rho when I use dm equals lambda dl, dm equals sigma dA, and dm equals rho dV. I'm just getting a lot of feedback from my students that suggest they don't necessarily understand what I'm talking about when I say lambda or sigma or rho. This one doesn't show lambda, but other examples might. So let us begin. The x center of mass is equal to the integral of excuse me, I was thinking moment of inertia for a second there, is equal to x dm divided by the integral of dm. What I'm going to do is handle the top integral first. So the integral of x dm is equal to, what I have to do now is choose a dm such that the x coordinate of it does not vary macroscopically from one part to another. So if I were to choose, for instance, let me just show you this. If I were to choose a shape like this, you can see that the left end and the right end have a major discrepancy in their x value. The x value of the left end is macroscopically different from the x value of the right end. I don't want that. If I had something like that, I would have to figure out some kind of averaging process to make a representative x value of that particular coordinate. So it's typical for us to take a differentially wide itty bitty section like that. So that's what I'm going to do. I'm going to draw the little section on here. And because it has a infinitesimal width, specifically, we would say this coordinate is x, or this abscissa of the point, for instance, is x, and this one is x plus dx. And that's just showing you that the width is, in fact, dx. It also shows you that the x coordinate of this should be essentially x. You could call it somewhere between x and x plus dx, but we're taking the limit as dx approaches 0. So ultimately, any difference between x and dx is not going to really matter. We are going to calculate that, but in order to calculate that, we have to say this object is our differential mass element, and we have to use one of the formulas, dm equals lambda dl, dm equals sigma dA, or dm equals rho dv to calculate what dm is. So what I'm going to do is I'm going to say dm is actually equal to sigma times dA, and dA is just supposed to be the differential area element that I've just chosen. So I've chosen a vertical rectangle as the area that we're looking at, and therefore its differential area is basically the width times height, where obviously the width is differential. So we're going to say this quantity is sigma times dA, which I'm going to call y, meaning the height is actually y, and the width is dx. So this quantity right here is dA. Now, I also need the x coordinate of that particular quantity. And the x coordinate obviously is x, but we also need to understand what the y is here. So we're going to have to figure out when I say y as the height, I have to have some understanding of what that y height is. That being said, let's go ahead and compute the integral. We've got the integral of x dm is x times the sigma of y times dx. Well, y is the actual function. In other words, the height, it's a function of x. So we've got to actually compute what that y of x is. Specifically, what we can do is we can recognize that this line right here is a straight line and it goes through the origin. So using y equals mx plus b, which is the equation for a linear graph, gives us y is equal to rise over run. The rise is clearly h, the run is clearly w, and then x. So that's y equals mx, and the intercept is 0. So we are going to actually, we are going to actually plug in that for y, so I get the integral of, I don't know why it switched to purple. I do know why it switched, but I thought I'd switched it back actually. So it's the integral of x times sigma times, as I said again, it would be h over w x dx. So what uh, that is actually our full integral that we have to deal with. Now we can see the sigma, the h, and the w are all constant, so I can pull them out in front, and I'm going to have sigma h over w is equal to the integral of x squared dx, and we're going to integrate from x equals 0 to w, and that, of course, gives us sigma h over 3w times w cubed. Almost wrote w squared there. So again, the integral of x squared is just 1/3 x cubed. And when I evaluate that at w, I get 1/3 w cubed. And when I evaluate that at 0, I get 0. So this is the total result for the top integral. Now I'm going to complete the bottom integral in a similar fashion. So the integral of dm is going to be equal to the integral, in this case, of sigma times dA, which I'm going to use the exact same sigma and dA. That's going to be sigma times y dx. But again, the y is given by h over wx times dx. So pulling all my constants out in front, I get sigma h w times the integral of x dx from x equals 0 to w, and this just becomes sigma h over 2w times w squared. Again, the integral of x in this case being 1 half x squared. When I evaluate 1 half x squared at w, I get 1 half w squared. When I evaluate 1 half x squared at 0, I get 0. So now I can combine these two results to compute the x center of mass, and the x center of mass becomes sigma h over 3w times w cubed. Obviously, I could have made some simplifications before I did this, but I didn't, so it's okay. We'll just do it now. Oops, there I go, erasing again. So now I'm going to take the bottom, which is sigma h over 2w times w squared. We can see a lot of cancellations here. For instance, this w squared cancels out with this w down here and leaves a 1 up there, and this w cubed cancels out up there with this w and leaves a 2 up there. This x actually, or excuse me, this h actually cancels out with this h, and this x cancels out with this x. So ultimately, all I'm left with is w squared over w, which is just plain w. The h is canceled out, and I get 2/3 w. Oops. And that is actually the general result, specifically speaking. If you have a triangle that is uniform, has its mass uniformly distributed, the center of mass would be 2/3 of the way from a sharp pointy end to the thick, fatter end. So if I look and see the sharp pointy end is the end at the origin, and I see that the triangle is getting wider as I go to the right along the x-axis, then I reach the conclusion that I should be 2/3 of w to the right to get the x center of mass. Similarly, you should expect the y center of mass in this case would actually be at y equals 1/3 h, because that's 2/3 of the way from the sharp pointy bit at y equals h down to the fat bit down at y equals 0. So that's what we expect that result to be. We have one part of the problem solved, and it is xcm is equal to 2/3 w, and I'm going to box that off, and now we're going to work the y center of mass part. I'm going to steal some of this information to put on the next page. So I will circle all this stuff right here. Not that I needed all of that, but I definitely needed the diagram, and I didn't want to leave any parts out. So I'm going to copy this particular part and paste it right here. And again, we're treating it as a two-dimensional, so it doesn't matter that I have that there. The difference on this part, though, of course, is we're now calculating the y center of mass, not the x center of mass. So this is going to become y center of mass, and this value right here is going to become y. So in this case, the differential area element that I've chosen is not a good candidate. So I'm actually going to get rid of that as well. Let's just do it by erasing all of this. And of course, we can go back and make this a little neater by fixing the parts that we accidentally erased and other parts that have turned blue because they had blue stuff going through them. We just fix that up like that, and that's close enough for our drawing. I should say also I want to go ahead and take care of this Y part because that's not what we're dealing with here. So now what I need is I want to calculate the center of mass in the Y direction. And of course, the top integral is the first one we're going to work. And that top integral is the integral of Y dm. So I need to choose a differential y element, a differential mass element. But again, when you're doing integrals, it's important that you take the integrand and make sure it doesn't change by a macroscopic amount from one part of the integrand to the other. When you're integrating. Otherwise, you'd have to figure out some kind of averaging process to see what part of the particular y value is most indicative or most important for the shape that you're dealing with. So, like an average type process or something. So, in this case, I can't have y vary greatly like I did on the other one, which means I can have x vary greatly. So, what I'm going to do is imagine a differential area and differential mass element that might be a slice like that. You can see that a slice like that has a macroscopic change in x, but it doesn't have a macroscopic change in y because the bottom of that block would be just plain y and the top would be at y plus dy. So that is going to be our differential mass element and differential area element. So what I'm going to do is just draw the shape right here. It is a rectangle. And in fact, you can say that this differential mass element should be equal to sigma times dA. And dA is the actual area of that little block. Well, that block obviously uh, has the bottom coordinate at a position y and the top edge at a position y plus dy, and it has a width that's not really x. This, for instance, is x, but this is the dw. That's the width of this rectangle. Okay, so we really need to get dm in terms of that. So dm equals sigma dA, and actually I didn't write that very cleanly. dm is equal to sigma times dA can become specifically uh, d sigma times the actual dy and then times dw. So we are actually times the dy and times the dw. So the dy is the height, and the dy, which I just made up that name just to suggest that it's going to be something different, but technically it shouldn't be a differential. I just couldn't use the w because that was the variable that we used for it, but I got to figure out what it is. What I do know is that vertical line is x equals w. So we could say x is equal to, or I could say that differential width. Again, I'll put quotation marks around it so you don't mistake it as an actual differential. But that width, dw, is technically w minus the x coordinate. So we have to get x in terms of y if that's the case. So I'm going to say now that we have sigma times w minus x as the width, and then the dy is the height. So in order to actually express this, we need this equation for the hypotenuse of this right triangle. This equation we have in terms of x, y equals h over w times x. If we wish to represent that as a x as a function of y, all we have to do is solve it for x. So if we take y equals h over w times x, and we solve that for y, all we have to do is multiply both sides by w over h And what we get is W, oops, it's supposed to be blue now. What we get is W over H times Y is equal to X. So that's what we're going to replace the X with. Now I can go ahead and plug in the rest of my results into the integral that we're doing, which is the numerator integral. So this is going to be the integral of Y times dm, which we figured out was sigma times w minus x times dy. And of course, we figured out that the sigma is a constant, so that can definitely come out in front. But we also figured out that the x is a function of y, so this is going to become w minus w over h times y times dy. We are going to integrate this from y equals 0 to h, and we proceed as follows. So I can go ahead, for instance, and break this up into two integrals. We could say it's the integral of sigma times the integral of y times w times dy, again from 0 to h, minus sigma times w over h times the integral of y squared dy. Just make sure I did everything and got all my terms there. The sigma's there, the y and the other y is there, the w over h is there. That all looks good. So this is going to be an integral from 0 to h. And in this case, we get the integral of y dy is just 1/2 y squared, which we evaluated at h to give us 1/2 h squared. So for the first integral, I'm going to get sigma times w uh, over 2 times h squared. And for the second integral, I'm going to get sigma times w over h. This one's going to be a 1/3 y cubed, which we evaluated at h will become 1/3 h cubed. So that's the actual result of these two integrals. Now I can simplify a little bit. For starters, let's do some cancellations of the h. We can see that this h to the third becomes h to the 2 when I cancel that out there. So now I have just basically sigma w h squared in both terms. So I'm going to write that out to the left, sigma WH squared. That's common to both of them. And then we have 1/2 minus, and I'm leaving these spaces for a reason because I'm getting ready to do some some fraction math. So with this in mind, we now have basically that it's 1/2 minus 1/3. Obviously, we want a common denominator. The least common denominator is 6, so we're going to multiply the 2 by 3 over 3. And we're gonna, oh, that was a bad parenthesis I drew there. And we're gonna multiply the 1/3 by 2 over 2. And in so doing, we will get sigma WH squared times 3/6 minus 2/6, which obviously gives you 1/6. So this result is going to be sigma WH squared over 6. That's just the top part. Now we're going to do the bottom integral. The bottom integral is the integral of dm, and we just use the same stuff we did before. So now I'm going to take the integral of sigma times w minus, it would normally be x, but of course we figured out that x was w over h times y, and then times dy. So of course, this integral is going to be from y equals 0 to h2. So we're going to pull the sigma out in front, and I'll get an integral from 0 to h of w dy minus the second integral is going to be sigma w over h times the integral of y dy from 0 to h. And that is going to give us sigma w, and the integral, of course, of a constant is just y in this case, and y evaluated at h is 0, and y evaluated at 0 is 0, or excuse me, y evaluated at h is just h, and y evaluated at 0 is just 0. So we're going to have sigma times wh for the first integral. And for the second integral, we're going to have sigma w over h times 1/2 h squared, again because the integral of y is 1/2 y squared, and then when we evaluate that at h, we get 1/2 h squared, and when we evaluate that at y equals 0, we get 0. So now we can see that this h squared will cancel out with the h in the bottom, leaving just a h to the 1 power. And we see that we now have a common factor of sigma times w times h for this integral. So I'm going to factor all that out and say sigma times w times h. But then we have 1 minus 1/2. Again, we're going to have to do some fractional work here. And the least common denominator between 1 and 2 is obviously 2. So it's going to be 1 over 1. In other words, we don't have to do anything to this one. But in this case, it's going to be 2 over 2. So multiplying by 2 over 2, we're going to get that sigma WH times 2 over 2 minus 1 over 2 is just going to give us, in fact, 1/2. So our final answer is, for this integral, our final answer is sigma WH over 2. Now that means y center of mass is equal to the top integral, which we found was sigma h, or excuse me, sigma w times h squared over 6 divided by sigma wh over 2. In this case, you can already see that this h cancels out with that exponent of 1 leaving, or exponent of 2 leaving an exponent of 1. This w cancels out with this w, and this sigma cancels out with this sigma, and the 2 actually comes to the numerator and the 6 comes to the denominator. And I didn't write this very neatly, so I'm moving the YCM. I'm moving the YCM better in line with it. So now what I have is just a H on top with a 2 next to it, and then nothing on the bottom except for a 6. And you can recognize this as 2 6 is the same thing as H over 3. So we finally have that the X center of mass, Y center of mass of this particular triangular plate is in fact 2/3 W. Oops. Darn it, why does it keep doing that? Is in fact 2/3 W for the X coordinate, and then 1/3. There it goes again. And then 1/3 H for the Y coordinate. And we're done. That is the way we go about calculating the center of mass as if this is a two-dimensional object. If you wish to do it as a three-dimensional object, you would have just used, instead of sigma dA, you would have used rho dV, and the dV would have been basically only different from the dA by an added factor of T, where T is the thickness. So notice I also never used the density. I actually never had to calculate what the density was. I did in the first instance specifically so you would have some understanding of what those densities mean, but I never used it. They all just canceled out. Everything was fine. So I hope that helps you better understand how to use integrals to calculate the center of mass. And that's it. Bye-bye.